Hello everyone, welcome to my talk on our ApproxDet work, Content and Contention-Aware Approximate Object Detection for Mobiles. My name is Ran Xu, and this work is jointly done with Chen Lin, Peng Cheng, Jay Yong, Subrata, Professor Chatterjee, Professor Li, and Professor Baiqi. We are from Purdue University, Nanjing University, University of Wisconsin-Madison, and Adobe Research. Our work focuses on the object detection on streaming videos, which is one of the most important vision tasks, and there is a great need to run it on the mobile devices. The detection kernel of our system is based on FastRCN, and I would like to start with this well-known detection framework to gradually introduce ApproxDet. FastRCN featured with a two-stage design, identify the region of interest from the feature maps in the first stage, and classify and localize the object in the second stage. However, FastRCN are computationally expensive. After FastRCN, researchers design new models to reduce the computation costs and maintain the accuracy. YOLO, SHG, and MobileNet are such works either for object detector or the feature extractor. However, the computational cost for object detectors is still high for mobile devices and limits its application on streaming videos. For the video object detection task, system community has come up with the hybrid design with object detector on some keyframes or every n frames, followed by the object tracker on remaining frames. H-Cloud is also used to offload the heavy computation. MCDN is another related work who introduced approximation to the DN-based framework under resource constraint. MCDN creates a bag of models and selectively chooses a model to execute, either on-device or on the cloud. Despite the overwhelming lightweight design, either generally or specifically for mobiles, these models are static models with fixed computation costs and fixed accuracy on some dataset after the architecture is designed and the models are trained. We identify the key challenge that these static optimizations or lightweight design cannot adapt to the runtime condition on mobile devices. The first example is the resource contention on the device. For the resource contention here, we refer to the reduced performance due to resource competition from other concurrent applications. As you can see in the left figure, we compare ApproxDet with a baseline solution on object detection by gradually increasing the contention level on the GPU cores of the mobile devices. The baseline solution's latency increased by up to 70% and violates the latency requirement with 40% plus GPU contention, while ApproxDet is always strictly below the latency requirement. Here, 40% contention means that the 40% GPU resources is taken by other concurrent applications. We can also see on the right figure that ApproxDet, though sacrificing its accuracy, is still better than the baselines. The second runtime condition comes from the video content itself. We show the latency of the object tracker can increase significantly with more objects and larger objects in the scene. The movement of the objects has impact on the accuracy as well. Finally, the static model cannot adapt to the latency requirement changes as well. Our measurement shows that reloading a model can take 5 to 20 seconds on the mobile devices, which is unacceptable for latency-sensitive applications like streaming videos. To solve these problems, we first propose a multi-branch detection framework. We show here a typical solution for the video object detection problem that combines a heavyweight detection DN and a lightweight object tracker. We propose to expose the tuning knob in such a detection system first. We set the FastRCN as a detection DN and modify it to accept the input video frames in dynamic shapes and work with different number of region proposals as another tuning knob inside. We set the 4 different object trackers and make the object tracker work on downsampled video frames in shape as well. Also, the frequency, or called sampling interval, of the detection DN is tunable as well. Finally, combining these tuning knobs, we have thousands of runtime execution branches to adapt to the runtime conditions. Note that we particularly care the switching overhead when we select these tuning knobs and choose those with very little switching overhead. The second step is to design a lightweight scheduler that makes the runtime decision on which branch to run. The key design logic is that the scheduler needs an estimation on the accuracy and the latency of each execution branch. So we have the accuracy and the latency models. To make such prediction accurate, we have the content-aware feature extractor and contention sensor to extract the key features that have the most impact on the accuracy and the latency. Next, let's have an overview of the detailed technical problems to solve. We summarize them into 4 topics: the goal of the scheduler, the accuracy and the latency models, the contention model, and controlling the overhead. Due to the time constraint, we will only discuss the first 3. First, let's define the goal of the scheduler, or overall ApproxDet. The scheduler decides on which branch to run, given latency requirements that should be satisfied in 95% of the cases. To find such branch, ApproxDet found all approximation branches that satisfy the latency requirement, and then choose the most accurate branch, if any. Otherwise, it will choose the fastest branch. The runtime estimation of the accuracy and the latency is the crucial part to make ApproxDet successful. We propose the feature-based prediction models on the accuracy and the latency. The features include the approximation choices on the tuning knob, the metadata of the video frame, like height and width, the content characteristic, like number and sizes of the object and movement, and the contention feature like the CPU, memory bandwidth, and GPU resources that is taken by other applications. The overhead is also included in the latency estimation, so that too frequent branch switch will be penalized. ApproxDet treats the contention in the black box fashion. Especially, we assume that ApproxDet has no information or control on the concurrent applications on the device. So it treats the overall impact of them as a black box. ApproxDet sends the contention level by observing its impact on the latency of the current execution branch, and then use the sense contention level as the input feature of the latency model as we mentioned earlier. We also design a synthetic contention generator as a tool to generate CPU, memory bandwidth, and GPU contention in a more flexible and controllable way. This is a stand-in for background applications in the evaluation. Note that the ground truth contention levels in the synthetic contention generator are kept secret to ApproxDet according to our black box standing. For evaluation, we use NVIDIA Jetson TX2 board as the stand-in device for mobiles. We evaluate on the ImageNet large-scale visual recognition challenge dataset in 2015 for video object detection. We report the latency as the execution time from a video frame being loaded into memory to a detection output is made, and the accuracy as the mean average precision on the test video dataset. For baseline, we have 4 covering different aspects. We have FastRC as a representative of multimodal object detector. This baseline comes with 28 models with different input shapes and number of proposals, and our simple scheduler to choose the proper model to meet the online latency requirement. We have FastRC and a medium flow tracker, which is an example of object detector plus tracker, with the former running every n frames and later running in between. At the scale is the third baseline, which implements an adaptive object detection framework, adjusting input scale dynamically. and we also compare with ULV3, a light and accurate object detector. We first examine the accuracy versus latency trade-off between ApproxDet and baselines. We can see ApproxDet lies on the most accurate and fastest region of the figure, which is better than faster RTCN plus median flow and ULV3 baselines, and much better than other baselines. With this zoom-out figure including all baselines, we can also observe that the latency of either scale and faster RTCN baselines can increase by up to 2.5x with 50% GPU resources used by background applications. We then zoom in this figure and compare ApproxDet with its most competitive baseline, faster RTCN plus median flow and ULV3. We see that without the resource contention, ApproxDet achieve 11% and 9% higher MAP over faster RTCN plus median flow and ULV3, given the same 80 millisecond or 170 millisecond latency requirement. With 50% GPU contention injected, we see a slight accuracy drop of 2% MAP in ApproxDet, and a significant latency increase in faster RTCN plus median flow baseline. The latency increase will violate the latency requirement and be equivalent to a large accuracy drop if the baseline can switch to a light branch to mitigate the effect of contention. We also show a case study here on how ApproxDet adapts to the resource contention. On the left figure, we use a synthetic contention generator to inject a gradually increasing GPU contention from 0% to 60% throughout an 800 frame video. We set the latency requirement as 100 milliseconds per frame and observe the temporal latency. We can see that the blue curve, which stands for ApproxDet, is always below the latency requirement. We compare with faster RTCN plus median flow, whose object detector runs every 20 or 50 frames. The results show that the baseline with shorter detection interval will violate the latency requirement, and the baseline with longer detection interval, though safe, has lower accuracy. On the right figure, instead of using synthetic contention generator, we run the Gaussian elimination app on the background to simulate real contention. We see in the figure that at 200th frame, when the Gaussian elimination starts running, ApproxDet's latency spikes and quickly falls back to normal owing to its adaptability. However, the faster RTCN plus median flow baseline have the similar results, being either too conservative or too aggressive. We have identified some future work to make ApproxDet even better. Firstly, we can use reinforcement learning-based approach to design a policy network for the scheduler and train it together with the detection framework. Secondly, with more OS privilege and measurement, we can better study the contention and make better latency prediction. Finally, the propagation effects of ApproxDet to other applications are also interesting topic to study. Finally, here are the takeaway messages. In our ApproxDet work, we want to emphasize that object detection framework should be adaptive to the runtime conditions on the mobile devices, such as resource contention, video content characteristics, and latency requirement changes. We design a multi-branch detection framework and a content and contention-aware scheduler to dynamically adapt to such runtime conditions. Our evaluation has shown that we have a slight 2% MAP drop with half GPU resources taken by concurrent applications, and always satisfy the 95th percentile latency requirement, while the baselines do not. Thanks for listening, and I'd like to take any questions.